In a world increasingly connected, monumental structures rise as testaments to human ambition. Among them, the Akashi Kaikyo Bridge stands as an unparalleled icon, not merely for its breathtaking scale, but for the profound engineering ingenuity required to erect it. Spanning treacherous waters notorious for their volatility, this bridge isn't just a crossing, it's a fortress against the raw power of nature. Its story is one of unprecedented challenges met with equally unprecedented solutions, forging a path where none seemed possible. Located in Japan, the Akashi Kaikyo Bridge links the city of Kobe on Honshu Island with Iwaya on Awaji Island, crossing the Akashi Strait. This strategic connection was vital for regional development and transportation, yet the strait itself presented a formidable barrier. Spanning an impressive 1.99 miles in total length, with its central span alone stretching 1,991 meters, 6,532 feet, it claimed the title of the world's longest suspension bridge. This colossal scale demanded engineering solutions far beyond conventional approaches. The Akashi Strait is not merely wide, it is a battleground where nature frequently unleashes its full fury. The region is notorious for its typhoon-prone waters, bringing gale-force winds and churning seas that could shatter lesser structures. Compounding this atmospheric threat is its location within one of the world's most seismically active zones. Japan experiences thousands of earthquakes annually, making the threat of a major seismic event a constant, critical consideration for any large-scale infrastructure project. This combination of wind and seismic activity presented an extreme design challenge. The first colossal hurdle was establishing stable foundations in the deep, turbulent waters of the Akashi Strait. Traditional pile driving was insufficient. Instead, engineers opted for an innovative approach, constructing massive steel caissons on land, floating them into position, and then sinking them precisely onto prepared seabed. This process was exceptionally complex, requiring meticulous planning and execution to counteract strong currents and ensure perfect alignment for the towers that would eventually rise from them. The caissons, each a monumental structure in itself, were submerged using a precisely controlled method. Water was gradually pumped into their chambers, allowing them to descend evenly onto the seabed. Divers worked in challenging conditions to prepare the foundations and guide the caissons, ensuring they settled firmly onto the bedrock. This stage of construction was a race against the elements, where any miscalculation or delay could spell disaster, especially with the constant threat of unpredictable weather systems moving through the strait. The precision required was almost unimaginable at this scale. Constructing such a massive bridge in typhoon-prone waters demanded innovative solutions for worker safety and structural integrity during adverse weather. Construction schedules were meticulously planned around weather forecasts, but sometimes the unpredictable nature of typhoons meant work had to continue under challenging conditions, or be halted entirely. Specialized equipment and protocols were developed to secure materials and partially completed sections against high winds and waves, minimizing damage and ensuring worker safety. This constant battle against the elements defined much of the bridge's construction phase. The heart of any suspension bridge lies in its main cables. For the Akashi Kaikyo Bridge, this meant spinning two colossal cables, each 1.12 meters, 44 inches, in diameter. This was achieved through an innovative aerial spinning method, where individual high-tensile steel wires were strung across the strait, one by one, then bundled together. This painstaking process, carried out hundreds of feet above the churning waters, represented a pinnacle of precision engineering and logistical coordination, ensuring the strength to support the entire bridge deck. Each of the two main cables is comprised of an astonishing 290 individual strands, and each strand contains 127 high-tensile steel wires. This means a single main cable alone is made up of 36,830 individual wires, totaling over 300,000 kilometers, 186,000 miles, of wire if stretched end to end, enough to circle the Earth nearly 8 times. This incredible density of high-strength steel is what gives the bridge its unparalleled load-bearing capacity and resilience against the constant forces of wind and gravity. To combat the immense forces of typhoon winds, the Akashi Kaikyo Bridge incorporated advanced aerodynamic design. Unlike solid bridge decks, the bridge utilizes an open truss deck structure. This design allows wind to pass through, significantly reducing the uplift and drag forces that could cause dangerous oscillations. Additionally, vertical stabilizer fins were integrated along the edges of the deck, further enhancing its aerodynamic stability and preventing wind-induced vibrations, a crucial innovation for a bridge of this unprecedented span. Given Japan's seismic activity, earthquake resistance was paramount in every aspect of the bridge's design. The philosophy centered on allowing flexibility while maintaining structural integrity. Engineers designed the towers, foundations, and deck to absorb and dissipate seismic energy rather than rigidly resisting it. This innovative approach ensures that the bridge can sway and move with ground tremors, preventing catastrophic failure. The Akashi Kaikyo Bridge became a living laboratory for advanced seismic engineering principles. In January 1995, during the bridge's construction, the region was struck by the Great Hanshin earthquake, a magnitude 6.9 tremor. This devastating event tragically claimed over 6,400 lives and caused widespread destruction in Kobe. Miraculously, the partially completed Akashi Kaikyo Bridge, still without its full deck, withstood the quake. The seismic forces caused the South Tower to shift by approximately 1 meter, 3 feet, relative to the North Tower, unintentionally increasing the central span by about 1 meter. This real-world test provided invaluable data and validated the inherent resilience of its foundational design. The earthquake presented an unforeseen challenge. The two main towers were now a meter further apart. Rather than dismantle and rebuild, engineers demonstrated remarkable adaptability. They recalibrated the design of the bridge's main cables and deck sections to accommodate the new, slightly extended span. This rapid and ingenious adjustment not only saved immense time and cost but also cemented the bridge's reputation as a structure capable of evolving and adapting, a testament to the flexibility embedded in its original seismic design principles. The two main towers, soaring 283 meters, 928 feet, above the water, are not rigid monoliths but are designed to flex. Each tower consists of two steel columns connected by cross-bracing, creating a flexible structure that can absorb and distribute seismic energy. This segmented design, coupled with advanced damping systems, allows the towers to sway several meters in any direction during an earthquake or typhoon without suffering structural damage. It's a dance with nature, where movement is strength. At either end of the bridge, immense anchorage blocks secure the colossal main cables. These structures are not merely passive weights, they are massive concrete and steel fortresses, deeply embedded into the bedrock. They are designed to withstand the immense tension of the main cables, which can exceed hundreds of thousands of tons, ensuring the stability of the entire suspension system against the constant pull of gravity, wind, and seismic forces. Their sheer scale reflects the extraordinary stresses they are engineered to manage. The scale of innovation, the materials, and the sheer effort required to build such a structure came with a significant price tag. The Akashi Kaikyo Bridge ultimately cost approximately $4.3 billion to construct. This figure, while substantial, reflects the investment in cutting-edge technology, rigorous safety protocols, and the unparalleled engineering expertise needed to overcome the extreme environmental challenges of the Akashi Strait. It stands as a testament to what nations are willing to invest for critical infrastructure and engineering triumph. The Akashi Kaikyo Bridge, with its central span of 1,991 meters, 6,532 feet, holds the record for the longest central span of any suspension bridge in the world. This achievement places it in an elite category, far surpassing its predecessors and peers. While other megabridges might have greater total lengths, the challenge and engineering complexity are often concentrated in the uninterrupted central span. Its immense length is a benchmark for what is possible in long-span bridge engineering. The construction of the Akashi Kaikyo Bridge provided invaluable lessons for future megabridge projects worldwide. The innovations in aerodynamic design, seismic resistance, and deep water foundation techniques have become benchmarks for engineers tackling similar extreme conditions. Its successful completion under immense pressure demonstrated that with enough ingenuity and resources, even the most daunting natural obstacles can be overcome, pushing the boundaries of what was once considered impossible in civil engineering. Even after construction, the bridge requires continuous vigilance to maintain its structural integrity against the relentless forces of nature. Advanced monitoring systems constantly track its performance, detecting any subtle shifts or stresses. Regular inspections, painting cycles, and cable maintenance are critical to ensure its longevity. The engineers understood that a triumph of construction must be followed by a commitment to enduring maintenance, safeguarding this vital link for generations to come against corrosion, fatigue, and environmental wear. The Akashi Kaikyo Bridge is more than just a passage, it is a powerful symbol of Japan's engineering prowess and unwavering resilience in the face of nature's might. It stands as a testament to the collaborative spirit and relentless pursuit of innovation that defines human ambition. Its story, deeply intertwined with overcoming extreme conditions and adapting to unforeseen challenges, continues to inspire engineers and dreamers worldwide, reminding us that with enough determination, even the grandest visions can be anchored in reality.